All right, so yeah, I am this Julie Moronuki, who wrote Haskell Programming for First Principles. For those of you who don't know, Haskell is my first language. Sort of writing the book was how I learned Haskell, which is a strange way to learn a programming language. I was never a programmer before that, so there's a lot of things about sort of general programming skills and other programming languages and stuff that I still don't know. I'm learning, but I am kind of Haskell specific. I will do my best to help you with any other question that you have, but I'm kind of Haskell specific. Sorry. All right. Yeah, I had several people ask me to do a workshop like this because you may have noticed a lot of the guides who are here this time are Haskell people, and there's a lot of category theory and stuff going on. I don't know how much of the category theory will necessarily be Haskell specific, but for some people who are not used to thinking about types and type classes in the way that Haskell people do, this is going to be kind of an introduction to that. So, do you already have Stack installed? Stack and GHC? I know you do, Adam.
I did the reading, I promise.
Does everybody else have Stack? Does anybody not have Stack installed? You're going to want that for other workshops here as well. So if you don't, okay. Do you have you done a Hello World with Stack to make sure that all of your environment is working properly? If you haven't, you can do Stack new Hello Simple, and that'll, like this. Stack new Hello Simple like that, and that will install a little Hello World program. It installs a Stack template and a Cabal file and everything for you, and a little Hello World program, and then you can check to make sure everything got set up right by running stack build, and then stack exec hello, and it should say hello world to you. Is everybody comfortable that they're set up properly? Yes? Cool. If not, you can go ahead and do those things, but I'll go ahead and start talking. Okay, how many of you, other than Adam, how many of you have written some Haskell before? Okay. All right, so some of this might be review for you, and so maybe we can, so hopefully it won't get too boring, but we'll try to make some good progress. All right. So in Haskell, all values have a type and all functions have a type. We won't go into right now what a function is. I'm going to assume that you have an idea of what the difference between a function and a value is, although functions are also values. And so everything has to have a type, right? The types are static. They resolve at compile time. And for the most part, unless you're doing something really weird, they can't just change. Once they're set, they're set. So we have two basic categories of types. In Haskell, we have sum types and we have product types. So these are some examples of sum types. This data here, this is a keyword that introduces a data type declaration. Okay, so the most basic sort of sum type there is we have represented here by bool, because pretty much everybody understands bool. And bool has two possible values, false or true, right? So the pipe, as is often the case in Haskell, the pipe represents disjunction, right? In this case, it's an exclusive or. You either have a false or a true, not both at the same time. Okay, so the name out here, bool, is capitalized, as it must be, and that's what we call a type constructor. That's the name of our type. These here, now with bool, we can call them data constructors, but they don't really construct anything, right? They're just constant values. But they're also capitalized, and these are, okay, so bool, your type constructor, is what would appear in a type signature, whereas these are what would appear at in your as values when you implement a function, right? Okay? So we've got on this side a type constructor, which is only used in types and type signatures. And these are the values. All right, so the next one we have is maybe. Now maybe is a sum type like bool, but you see that it takes one parameter, right? All right, so what can the A be? The A is a type variable, so what could the A be?
Any type.
Any type, right? Any concrete type. Okay? All right, then on the two sides of maybe, we've got nothing, right? Which is just a value again, but it's not parameterized. Or we have just A. What is that A in the just?
So the type of type A.
Type probably.
Yeah, it's got to be something of the same type as this A, right? The A has to be the same throughout. I mean, over here, this would be a value inside the just, right? But a value of the same type that this A is, right?
So it'd be, think of it, that A would be a member of
Right.
A. Okay.
Yep, a member of A. All right. Now, either is also a sum type, but this one has two parameters, right? We've got A and B, and the left constructor of either contains the A, and the right constructor of either contains the B. All right, so what do we know about either then? What are A and B? Do they have to be the same type?
No.
Can they be the same type?
Yes.
Yes, they can. Right, so you could have either, string, string, and then this would be a left, some string, right, and a right, some string, right, and that would be fine. But they can be different, right? All right, and at the bottom we have the data type for list. So list is a little bit strange. It's like tuples, where we have a little bit of baked-in syntax here. But this is the actual data type definition, right? So on one side of the sum, we have the empty list. And on the other side, we have this, which is a product, right? It's a product of an A and a list of A, right? So given this type signature, can we have heterogeneous lists? Can we have lists that have values of more than one type? No, right? Every A inside the list has to be the same type, right? This here, in case you don't know, this is the cons operator. It's an infix operator that builds lists. If you do get around to writing recursive functions yourself in Haskell, like if you're trying to write map or something by yourself, or sum or something like that, you need this guy to rebuild your lists. Does that make sense? So that's actually an operator that's building a list, that's consing a list on, right? So this is also a recursive data type in that you can keep consing new A's into your list for as many A's as you have, right? So there's a limit on what types can be in your list, but not a limit on how many of them there can be.
I have a question here.
Yes?
On this last example, A is inside the square brackets and on the term on the right.
Yes.
As opposed to be after the square brackets.
Yes.
What's the rule there? I expect to be square brackets A instead of being inside the square brackets.
Well, so the A is inside the square brackets because the values that are in here have to be of type A, right? So it's not saying that it's not a, how to put this? It's, if you have a list that's not empty, then you've already got something inside the square brackets, right? So this is just saying that you can have only a one element list, right? But you can also keep consing more stuff into there. So the other option is an empty list. You've either got it empty or you have at least one value of type A inside.
So does the cons operator mean that I've got that listed A and the A colon means I can put in a number of more A's into it?
Yes.
Okay.
So it's either empty or has at least one A in it. Right, that's what this means. It's either empty or it has at least one A in it.
Like, I guess, why wouldn't the syntax be empty brackets, pipe, and then A in brackets?
Because you want to have this infix operator here to tell you that you can keep putting more A's in.
Okay, so I'm saying consable.
Yes. Yeah.
Oh, okay.
That's what makes it a recursive type, right?
Yes.
Okay.
Yep, exactly.
So that operator is part of the type.
Yes. But we can also use it at the term level in functions.
Okay.
Yeah.
But I guess my question is, if we declare it as list A, let's say data list A is equal to new or cons A list A,
Yes.
but there is not list A, is open square A whole square. Why is not the square brackets and then A? Why is it infixed in the square brackets and not postfix?
I mean, really the answer is just because that's how the syntax is defined in the compiler. Is really the answer.
Yeah, but
If you-
I was
if you-
looking for the rule of the syntax.
The rule of the syntax is that square brackets mean a list. And so if you've got, it's either empty or there's something inside of it. This is just the list syntax, the square brackets is just special syntax, and it's, if you define it yourself using a type constructor, then yeah, your type constructor is not, you can't do the same thing with it because it's not special syntax defined in the compiler that you can do this with. You could make an infix operator that builds a list, like cons, you could make your own, but it still wouldn't behave the same as the brackets do.
So there isn't a special exception in the compiler saying make lists look this way.
There isn't?
That's what I'm asking.
What do you mean?
So what you see a lot in other languages is I can create this type, whether it's this structure, which is like a hash map or whatever. But if I were to define that myself, it would look very, very different than what the compiler understands.
Oh yeah, if you define a list type yourself that is doing the same thing as this, but it uses some other type constructor, yeah, you won't get the square brackets.
Okay.
Yeah. Did that answer your
Yes,
question?
yes,
Yeah.
yes.
Okay.
I have another question.
Yeah,
The cons operator,
yes.
does that definition create the cons function, or is that also somewhere else in the code?
I think the cons function is actually defined separately elsewhere.
Okay.
Yeah. I'm not positive about that, but I think so.
Would it be valid to have that same declaration without the empty list or?
Yeah, so we do actually, there's a data type called non-empty that has no empty list constructor, and it can never be an empty list.
I mean, would that work with modifying that, or is that something different?
It's different because
Okay.
that obviously changes certain things about the way lists act, right?
Right.
Yeah. So suddenly, like with, since I know a couple of you know anyway, right? So like list has monoid instances, right? Because there's an identity value for lists, which is the empty list, but non-empty,
Okay, so I
Doesn't.
have to have an empty list or.
or you don't have a monoid,
Right, okay.
right? So
Thanks.
non-empty only has a semigroup because there's no identity value for it. So, all right. So let's look at some product types next. All right. So these are both kind of odd product types. but I want to look at both of them. So a product type, whereas sum type is a sort of disjunction of possible values, a product type is a conjunction of them. Okay, so this is how the two tuple or the pair is, the data type for those is defined. So again, we have some special syntax, kind of like the list syntax, this is different from the list one because now the A and B aren't inside the parentheses. I know, but that's just how they're defined in base, and I can't help that. So we have this type constructor, right, which is the parentheses with a comma in between, and that's what our tuple syntax looks like. Now we've got two type parameters, A and B. So a tuple, a pair anyway, right, is the conjunction of a value of type A and a value of type B, which just like with either can be the same type but don't have to be, right? Okay, and so the type constructor in this case is also the data constructor. We'll see in a little while that data constructors work a little bit like functions. They actually construct a value of the type when they take parameters. All right, and this is a very strange product type, but I wanted to go over it because we will be talking about it a little bit more later. This is the data type definition for the function arrow. So function is a type. It takes two parameters, or it has two parameters, I guess is a better way to say that, right? So what are those two parameters for the function type?
The input type and the output.
The input type and the output type, right? So you may have heard that in Haskell, every function takes one argument and returns one result. And so you can see that that is literally in the data type definition for a function. That's the only way it could be, right? There are only two parameters, one input, one result for every function arrow. Again, they can be the same type, but they don't have to be. And you'll also notice that this one is weird because there is no equals and then some data constructor out here, because what would the data constructor be? What does this type construct? A function, right? So the value that appears in term level is the function, right? All right, questions about these? Yes?
Could you have written the tuple and infix on the right side? Like you do with a list?
It actually won't, I think I've tried doing that before and I think the compiler got angry at me. I mean, this is how it's defined in base, so I think you would have to do it with some other syntax. Like if you could define a product type is what I'm saying with some other type constructor that is not special syntax and make it infix, I think. I haven't done it in a way that the compiler hasn't gotten angry at me, but yeah. I don't know why it's, well, no, I'm actually not really certain why this one is like that and list has the A already in it. Yes?
So the parens around the comma, does that not mean it's infix? Like that comma is defined as infix?
That the comma is defined as infix. No, this
confusing my concepts. I was just reading through Haskell book this weekend, and I thought it said the comma was to make things infix or not. Or sorry, the parens.
Right. Normally, yes. Not in this particular case. This is again kind of like the square brackets, where this syntax is just sort of special cased in the compiler, and this is. But normally, yes. If you put parentheses around like. Plus or the asterisk for multiplication, then yeah, it makes it prefix, right? It takes an infix operator and makes it prefix. And that's also how, if you need to query the type of addition, right, in the REPL, or even the function arrow, right? I don't have GHCI. So if you're going to query the type of them, then you also have to wrap them in the parentheses, right? So Yeah, you can actually, oops, you don't do type of function because that's already a type. But you can do info on function, right? And that's where you'll see the definition. So yeah, normally wrapping parentheses around something does mean that. Means that you've taken an infix operator and made a prefix. That's just not what it means in the special case of tuples. And you can make, I mean, of course there are also 3 tuples and 4 and so on, right? And then you get, because they can all vary, so then you get, you know, A, B, C, D for however many elements of a tuple you want. They are all different data types in Haskell, so there's if you get curious and you want to look at them in base, there's something like, I think they already have data types defined for up to about 60 element tuples. I don't know why you'd want a tuple that big. And there's a note in the comments in the source code for base that says, we tried to make bigger tuples and we got a seg fault. So, but they are each a separate data type definition because we can't just have one that is sort of, could vary in length, right? They're all fixed. Fixed arity. Arity is the word I'm looking for. All right, any more questions about these? We will look at some less unusual product types in just a couple of minutes. All right. All right, so with the sum type, because it's a disjunction of possible values, the cardinality, does everybody know what I mean by cardinality? The cardinality of a type? Okay, so the cardinality of a type is how many basically possible values there are of that type, right? So with bool, how many possible values are there? 2, right? So bool is relatively easy to reason about. You either have a false or a true. There's only ever 2 possible values, right? As you get more possible values, then the number of values you have to consider as possible, you know, inputs or results of your function grow, right? So things like integer and string, which are essentially just infinite, right, have infinite cardinalities, if we can even say that. But so the cardinality of a sum type, you figure it out by adding them together. When you have something like maybe, where there's a nothing or just a, then your cardinality is going to depend on what? A, right? All right, for a product type, what?
+1.
Yes.
Does nothing count in the cardinality?
Yes, nothing counts as 1. And so if you did have, if it was a maybe bool, then that'd be pretty easy to figure out. How many possible values do we have then? Right.
So the unvalued counts as a value.
The unvalued counts as a value, yes, because nothing is a value, right?
Okay.
All right. So the product type is a conjunction of 2 types, and the cardinality is multiplicative. Right, we multiply them to figure out the cardinality of a product type. So we have this, when we talk about monoids in a little while, because I'm hoping that we'll get through monoid enough that we can talk about why types themselves form a monoidal category, and that'll be like your introduction to category theory. Maybe we'll get there. All right, so because we have sum and product, right? We have disjunction and conjunction, right? So we're covering our Boolean possibilities, right? Okay, so, let's not talk about type classes yet. Let's go and look at this. All right, so we have some types here. Can everybody see okay? All right, so the first one we have here is colors, right? So we have 4 members of colors, right? These are not parameterized, so what's our cardinality? 4, right? All right, and how about for animals? What's the cardinality of animals? 2, right? All right, so now we have a product type that we want to define, right? For making various colored animals, right? So this is what a more normal product type looks like. Not like the tuple or the function arrow, right? So we have here our type constructor, and here's our data constructor. Now you're going to notice that they have the same name. That is fairly common in Haskell, and it can be really confusing at first. Okay? The type constructor, the compiler of course doesn't get them confused. The compiler doesn't care that they have the same name, right? But it can make things confusing at first. The type constructor will go, of course, in your type signatures, right? The data constructor here goes in your function or your values, right? This is what actually constructs a value of type Seuss. Okay? So to construct a value of type Seuss, we need one value of type colors and one value of type animals. And we don't have a value of type Seuss until we have one of each. Does that make sense? All right, so what's the cardinality of Seuss then? 8, right? Yep. All right, so your data constructor does not have to have the same name. So we could have put a different name here, but it does have to have, you do have to have a something here. You can't just say data Seuss equals colors animals, because then colors will not be referring to this type. It will just be the data constructor of Seuss. Right? Does that make sense? Yes?
How burned would that make you, because you also have a type that is colors and a data constructor that is colors?
Well, it wouldn't. The compiler wouldn't care about that, because it can distinguish between this one as being a type constructor and this one being a data constructor. Since you don't have a data constructor up here called colors, then the data constructor name and the type constructor name won't conflict. I don't think, I'm pretty sure.
No, they wouldn't, because
Yeah.
if you were to just delete Seuss from that, you would have a type constructor that takes animals and produces a Seuss.
Yes. Yeah, so your data constructor here could be named anything pretty much that you want. People just do this because sort of once you get used to it mnemonically, it's kind of easier to remember that, oh, I'm constructing a value of this type, so my data constructor that constructs that for me has just got the name of the type. All right. So down here, and you know, later I'll probably tell you not to do this, but this keyword here, this keyword here is for a type synonym or a type alias, right? And so I've just written 3 type aliases for strings, right? Which, you know, it's not great, right? Because strings are a problem, right? So, but we've got 3 type synonyms there for string. But they do at least let me name the 3 strings different things, right? So that I can then construct a data type that is a product, right? So I've got a sentence type that's a product of a subject, a verb, and an object, right? Okay.
But I don't get any type checking in that case. I could try to construct a sentence with verb, subject, object, and it would not complain because they're all just strings.
Because they're all just strings, yes. Yeah, you don't really get any, I mean, it helps you remember, right, what each thing is supposed to be. So you'll see this sometimes in, like when people are constructing like records of users or people or something, right? You've got a string called first name and a string called last name. So it helps you remember which thing is supposed to go where, but no. And you can give it, of course, obviously strings that aren't words in, you know, whatever language you'd be working in English or whatever, right? So, yeah. So it's not a good way to construct that. But then you get this nice product type. Does anybody want to tell me what the cardinality of this product type would be?
Scary.
It's horrifying, right? Yeah. So, all right, but a sentence then is a conjunction of the three things. So for S1, we will get type checking in the sense that, is there a problem here with S1?
This is a function.
Huh?
It returns a function.
It does return a function. It returns a function because,
Takes the object and returns the...
right, it needs one more argument, right? And so right now what we have is a partially applied function. So sentence here, in this case, this is the data constructor sentence, right? And in this case, it's a partially applied function, which is fine if you're going to go on and apply it to something else, right? But if you're just trying to show it, it won't show because it's still a function, because it hasn't been fully applied.
And Julia won't show because there's no show for a function that takes an object and returns a sentence.
Right.
I don't think that's a show instance for function, period.
There's not a show instance for function, period. One of the things, we're going to talk about type classes in just a minute, but I get that question a lot, why we don't just have show sort of instantiated for every type. And also I get that question a lot about equality, right? Because eq is a type class for equality. And the function type is the main reason why we don't have either of those baked into, just baked into every possible type. Because you can't have a equality checking for the function type, and you don't want to have a show instance for the function type. Mostly because it's not really law abiding in the sense that we think of, to the extent that we think of the show type class as having any kind of law. All right, so let's go back and talk about type classes. Are there any more questions about the basic types of types? We haven't touched on a couple of other things. That we have a product type that has record syntax, and we have also a thing called new type. They're not terribly important for right now. So, are there any questions about the basic types of types? Yes?
Type constructors are not functions, or are they?
Type constructors are not really.
I mean data constructors.
Data constructors are functions. Are essentially functions, yes. That's why, like in this case, when we're trying to construct S1 here, that's why we get this particular type error.
Oh, yeah.
Because we're trying to construct, because we have a partially applied function and we're trying to show it, and it won't show us a partially applied function. It won't show, meaning it won't print the partially applied function, right, as a string. So yeah, data constructors are like functions. So, in a very real sense. So tomorrow when we're looking at parsing stuff, you will see me mapping a data constructor over the results of some parsers, right, over some parsers to construct a value of that type, right? So you can actually map, or fmap is really what you want to do. Fmap a data constructor over and to construct a value of the type. All right, so, oops. What have I done? Okay. All right, so let's talk about type classes a little bit. How many of you are already familiar with type classes? Okay. So type classes, very briefly, are a record of functions or a dictionary of functions. They're not all functions, which is one of the differences between the way Haskell does type classes and the way some other languages do stuff like interfaces. They don't all have to be functions. So for example, there is a type class called bounded. And, sorry. And if you look here at the type class definition for bounded, bounded has two things in it, right? One of them will tell you the minimum bound of a type. The other one will tell you the maximum of a type. And they're just values, right? They're not functions. And so you don't apply them to anything. So how do you use them? Right? You ask for the max bound of, oops, like that. You just tell it, this little double colon here, for anyone who doesn't know, is how we assign types, right? And so you just assign a type to max bound, and it tells you. That's the maximum of the type int.
For
So-
that class definition,
Yeah. All right, so the type class is just a kind of record of not always functions. They are often functions. They're not always functions. Sometimes they're just values. When we talk about monoid, there's also a value in the type class monoid called mempty, and it's also just a value. But I hesitate to, I tried when we were writing the book to come up with some other way to put it, because you don't want to say functions, but you can't really say methods, because that has meaning for a lot of other people that's not necessarily the same as this meaning. So operations, expressions is better. Anyway, that's what type classes are. This is a kind of record of, or dictionary of things we want to do with a value of, with types. Which is real vague, but it's just hard to describe it without using some kind of other overloaded word. All right, so the class declaration, like we were just looking at the one for bounded. Oops, that's not what I meant to do. So the class declaration, like we were looking at for bounded here, starts with the keyword class. And that tells you that you're getting a type class declaration. Then it's got the name of the class. The A is for whatever type the instance will be for, right? So the A is the type parameter. And then you get basically just type signatures. That's what's in a type class declaration. Type signatures. So if we look for example at num. All right, so num is a type class that is implemented by a lot of numeric types, right? And so this is where addition is defined, right? Addition is a binary operation, right? So we've got A to A to A. They all have to be the same type, as you can see. We don't try to add two different types of numbers together. We have subtraction and multiplication defined here, negation, the absolute, some number, excuse me. All right, so negation and absolute just take one argument each, right? And return the negation or the absolute value of the number, right? So, but all we have here is the type signatures. So the way we know how to implement each one of those operations for the different types is in what we call instances. So here it lists some of the instances for num. So we have an instance of num for integer, right? And an instance of num for int, and for floats and doubles, so that we can add those together. So if you look at the instance, the num instance for integer, for example, it tells you how to add or multiply or subtract two integers. Okay, so that's where the function is actually implemented, is in the instance, not the class.
there
Yes.
be implementations for each of the operators.
Yes. In the instance, yes.
Is there a difference between integer and int in Haskell?
Yes. Integers are, int is limited, integers are not. And we have, there's actually several int types that you, so that you can limit them. There's int 8, int 16, int 32, right? Am I doing my math right?
Yeah.
Yeah. So int is limited, right? That's why we were able to do max bound for int, because it has a boundary, right? But for integer, it's just going to tell us that there's no instance for bounded because it has no boundary. Integer is infinite. Okay, so that's type classes and instances. The pairing between a type class and an instance should be unique. There should only be one type class instance for a given type. I mean, there's no, that was a bad way to say that. There should only be one instance of a type class for a type. So there should only be one num instance for integer. There should only be one eq instance for any type except for function, for which there should be 0. There should be, this is a little bit problematic when we talk about monoids, but for everything else, it is generally pretty easy to understand why there's only one implementation of that type signature that you want for that type.
If you don't follow that, does the first one win? Or does it fail to compile?
You'll get a compiler error, yeah, or a warning. Yeah. All right. So we're going to look at the eq class a little bit now. So the eq type class is where we implement equality. So one thing I said a minute ago is that you have to write in your instance, you have to write an implementation of everything that's in the type class for your type. That's not literally true. There's always a minimal complete definition. And then some of the other ones can be derived from that by default. So for example, when we are writing an instance for eq, we only really have to define equality. You don't have to define inequality separately, because it can just derive that, right? You can, if you're doing something weird, funky, you can define them separately, but you don't have to.
I think you only have to define one of them, yes?
You only have to, yeah, the minimal complete definition is one of them. It's pretty typical to just
Okay.
define equality. Yeah. You could only define inequality and then it'll derive equality, yes.
Right, okay, cool, thank you.
Yes.
Is there anything in the syntax that indicates this is the minimum that you have to?
No, you usually have to look that up.
Okay.
So you go and if you're trying to write an instance for your data type and you need to see what the minimal complete is, you have to go look in the base documentation.
If you go command info in the console, it will tell you minimal and the functions that you have to implement right next to it.
Well, it'll tell you all of them though, and you don't necessarily have to write all of them. I think it'll just tell you all of them. So like, I'm gonna have to import, huh? Where's alternative live? Control.applicative?
That sounds right.
Yeah, so like here, for this type class, sorry, this was just the first one that came to mind, but, so for this type class, alternative, this, I think the minimal complete definition for this type class is just the top two. You only have to define those. You can also define some and many if you want to.
Because if you do info for eq, it will tell you that actually you only have to implement double equal. It actually lists the minimal as well.
It tells you that?
Yeah, it looks like documentation.
But yeah, maybe it's just manually added, I don't know.
I'm not seeing that in
Oh,
mine.
interesting. My
Might be a
version of
different
Haskell.
Okay, mine shows minimal.
Yeah.
It does?
Yeah.
Wait,
Right, it shows the two functions, and then below that is a minimal double equal, or different.
are you using 8.1?
Yeah, I think I
that's the
have
case
I
on
think I
Windows
have
one.
installed.
I think my stack GHCI is 8. Let me, nope, it's still 7 on this machine
I'm
too.
on 801.
Dang it! Maybe they implemented that finally. That's really cool. Yay! That's awesome. So then you don't have to go look it up in the docs because it tells you. That's really cool. Thank you for telling me. I need to get 8 on this machine, I guess. All right, so for eq, we have to define at least one of these, right? We have to define at least one of these for our type, right? And you can see that it's going to take 2 values of the type that we're defining an instance for, return a bool value, right? So the type signature is given to us, and then we just have to tell it how to implement it, right? All right, so let us go and what did I do with it? All right. Oh, one thing I didn't talk about here because we hadn't talked about type classes yet is here I derived show. Right, eq is another one that you can just derive, so you actually don't write eq instances very often, but you do sometimes. You hardly ever write show instances by yourself because usually you just want it to just turn it into some string so that it'll print to the screen, right? So for this data type, I went ahead and derived show. For this one, I didn't. So what does that mean? What?
Oh, you're using the type aliases for send.
Oh, I am. I accidentally. Okay, well, we don't need that right now anyway, so. Alright. That must have been what happened when I accidentally deleted those. Alright, so if we try to print a color to the screen, right, then we don't have a problem with that. However, at the moment, we cannot do this, right, because we don't have an eq instance yet. But for animals, we can't even print it, right, because we don't have a show instance. So we'll go ahead and add show to each of these. But then for this one here, we'll add eq. And then for these ones, we won't derive eq. You'll write eq.
Cool.
Okay? So this one here, animals, is relatively straightforward. For Seuss, since you have a product of 2 other types, there's a little bit more complexity. You have an eq instance already up here. You have to have this eq instance for animals before you can get an eq instance down here. Or there's actually a way you could do it without doing that first, but you don't want to do that. Just write an eq instance for animals first, and then write an eq instance for Seuss. Yes?
Can everything get a default show capability?
Yes, pretty much, except for function.
Okay.
Yeah.
There are other weird cases, like I'm not sure if there's a show instance you could rationally make for like a database connection.
Oh, sure. I suppose there are other things like that that are, yeah.
But it'll still try to come up with something if you
It-
just say dragging show.
It might. I mean, I've derived show on some pretty weird types before, so I think it'll try pretty hard. You might not like what it prints out, but yeah. So there's several type classes that you can usually just derive. Show and eq are the 2 sort of big ones. Ord for things that have an order, like numbers and characters and stuff like that. Enum, but that only works for some types. There's a few others that we'll talk about. All right, so we need to write, so for our eq instance for animals, right, we want to start it like this, eq animals, where? All right, and then we're going to define how that function, which has a type signature A to bool, how that should work for this type. Sorry, my parents are supposed to be coming to pick up my kids. So, arranging that. Yes?
So should I have already seen enough information from what you talked about to be able to write this?
Possibly not. It depends on, and I'm going to go through how we do it in just a second if you want to just wait. So we have people with different amounts of exposure to Haskell already, and so if you don't have
It's
that.
not necessarily based on things you've already talked about.
No, no. All right, so you can write it like this where it's prefix. What do we have? Dog equals, and we need to return a bool, right? Or you can also write it infix, and that should still work. Okay, so now we've told it what to do when the two inputs are dog and dog. That's when we want to return a true, or cat and cat, and we want to return a true. Is that enough information?
That's saying any dogs would be equal to each other. Is that?
Yes, because we only have dog,
Okay.
right? So anytime it sees dog now, it's going to say that dog and dog are equal to each other, right? But is this enough information for our instance?
No.
Right, we still have, it's a partial instance, right? We still have a partial function here because we haven't told it what to do if the two inputs are not the same thing, right? So we will do that the Haskell way. Like this with the underscores. So the underscore means anything else, right? It means we don't care what else comes in as input. We don't care about the specific details here. Anything else that is not dog, dog, or cat, cat, anything else return false. Yes?
Order matters here, right?
Yeah, you have to do that last.
You do have to do that last, yes.
Because if you did that first, it would say, oh, well, nothing is equal to each other, you're done.
Yes. As a general rule, you want your most general case, your catch-all, your anything, your otherwise case to be the last thing because yes, it will read them in order, and if it catches the first case is your general, otherwise everything, catch everything case, then you'll just get false every single time. Thank you.
How does line 9 work exactly?
How does line 9 work?
Looks a little different than 8.
It does look a little bit different from 8, and let's make sure that it does work.
You can just do Control R, I think, or colon out.
Is that the last one I loaded? Yeah, okay, it was the last one, so. All right, so it compiled, so it must work, right?
Yeah.
That's the rule. But we didn't throw a type error, so we are happy about that. So we check it, and dog equals dog is good. Cat equals cat is good. Cat equals dog, we get false. So we're done here, right? So the way that works is that this operator, because it's not alphanumeric, because it's not alphabetic characters basically, so it's an infix operator by default, which means that in your instance you can write it infix, or you can put parentheses around it and write it prefix. Either way. I usually write mine prefix when I write instances, but not always. Like for Monad, I don't do that. Or there's some other ones, but for stuff like this, I usually put them prefix because look how nice that lines up now. And if we really wanted to be a good Haskeller, we would do that.
Now, if you really want it to be OCD, you would want it the second underscore with the capital letters on the other one.
Yeah, I know. That's how it is in the book.
Yes.
Yeah, we were really OCD about stuff like that in the book, but yeah.
You do underscore equals equals underscore for the last line, kind of like you did with
Yeah.
cat and cat. Okay.
Yes. Yeah, all the parentheses do, sticking it out here is just you're saying it's a prefix operator right now, but it's an infix operator by default, so it doesn't matter. You could rewrite all three of these with them,
In the middle.
yeah, and it would be the same. Now we need to get rid of those. and that will be the same. Right. So, and it should all work the same. All right. So has anybody already finished their eq instance then for Seuss? So we've got a conjunction of types, right? So we want to start this again. Instance, eq, Seuss, where, right? We've got a conjunction of two things that already have eq instances, right? So you can write this by literally taking the conjunction of the output of their eq instances, right?
So this whole instance should have like 3 lines in it.
Right. I mean, you can write out all the pattern matches if you want to, but you can just take the conjunction of their two eq instances. Okay, but here we're going to be comparing two values of type Seuss, right? So we're going to have a Seuss with a color and an animal. Is that, yeah. Right. Right, this is what we want to be comparing, right? All right, so if we want, we want to take, to figure out whether these two things are equal, we want to take the conjunction of if these two things are equal and if these two things are equal. Does that make sense? Am I doing it right, Adam?
That's what I had in my head.
Using the double E probably.
Huh?
Using double E.
Oh, yeah.
Yes.
All right, is it right now?
You need another one for otherwise. Oh, no, you don't. Right.
No, because it'll give us a false statement.
Right.
Yeah.
Okay. Don't listen to me, I'm one.
All right, it compiled, so we're good. Red dog.
You might need
Hello.
to paren that.
Huh?
You might need to paren that.
Maybe. We're
Let's
gonna
find
live.
out.
We're gonna live on the edge.
Oh!
Yeah, I don't think you do for eq. So. All right, so we have a working eq instance for our product type. Any questions about this? We know that our type signature here, right, has the type A to bool, and so we've told it how to take two values of type A, which in this case is animals, and give us back the bool value that we want for this. Yes?
Is there anything special about the apostrophes, or is that just a convention?
It's just a convention,
Okay.
yeah. Yeah, it's color and color prime.
Yeah.
Yes.
If you're, I'm gonna jump in over you. If you're coming in from other languages and you're thinking that's not a valid name character, the Haskell does it differently. That's completely
Yeah.
legal. So,
Yep, that is a legal part of a name, and so you'll see that a lot in cases like this. Yes?
Is that just to disambiguate where someone
Yes.
might say color and other color?
Yes. Yeah, you could name it something else, right? Like, so you could name it second color or, yeah. We just have to give the variables different names, right? Any more questions about this so far? All right. So when you go then to do something like this, when this is compiled, it sees that you've got a function from the eq type class, and it knows that you are calling on the Seuss instance for the eq type class, and it basically looks up how to implement that in the instance, right? All right. Okay, so let's go on and talk about type signatures and how to read them. All right, so we have a function, the name of our function in this case would be function, because we're creative. If we have a function that has a type signature that looks like this, right, what does this mean? How many arguments do we need?
2.
2 arguments. What type are they?
Integers.
Obviously, right? So what could this function be? Addition, yes, subtraction, multiplication. There's a lot of stuff this could be, right?
Even comparison.
Even comparison this could be. No, comparison will return a,
Boom.
it returns a greater than, equal than, or less than. Yeah. But there are a lot of things this could be. There's a lot of things that take 2 integers and return some other integer, right? All right. Now, part of the reason that this could be so many things is because we know a lot of things about integers, right? We know a lot of things that we can do with integers. In Haskell, part of the way that we know some things about this specific type is because we know what type class instances it has. It has type class instances for things like num, so we have a definition for how to do addition with integers, right? It has a type class instance for the integral type class, which gives us integral division operations and so forth, right? Okay, so that's part of why. When we have a concrete type, there's a lot of stuff that we know about it. We know what type classes it has instances for, or is instances of. All right, so there's a lot of things that this function can be. All right. On the other hand, when we have a type signature, which is more common, that has some polymorphic type variables, then we can implement the expressions without knowing what the types are, right? So when we have things like, when we look at the actual type of addition, right, here's the type class that it comes from, right, num A, and it's just A to A to A, right? So yes, we can do an addition that looks like integer to integer to integer, but we can also do a more general, we also can think of addition more generally as being an A to A to A, as long as those A's have instances for the num type. I mean, the num type class. All right, so so we have different kinds of polymorphism. We really have 2 kinds. There's parametric polymorphism, in which the type could literally be anything. So that's your A to A to A, right? Or, I mean, they don't have to be A's. A to B, that's also can be parametrically polymorphic, in which case those can be any type. When you have parametric polymorphism, the behavior of the function cannot change depending on what types the inputs are. Okay, so the classic parametrically polymorphic function is identity, right? Identity, we have an A to A, so it just takes one input of any type in the universe, any type you can conceive of. You can give it to identity, and what does identity do?
Returns itself.
It returns itself, right? What else could it do? Nothing, right? Because the behavior of it cannot change even if the type changes, right? because it is parametrically polymorphic. There's nothing that we know about A. We know nothing about A in advance, right? Because it
It's
could
like
be
Jon Snow.
anything. Yes. So
Wow.
There are,
So since we know nothing about A, then there's very little that we could say about it, right? Say about this function. There's nothing that we can do with this except for just return what we gave it.
there are two cases where we can cheat. We can loop forever and we can crash.
We can loop forever and we can crash, yeah. So those are things you could do with it. But things that actually work,
Yes.
Useful work.
yes, yeah. Things that will actually return an A, there's basically one, right? Things that will return an A value and not an exception or an infinite loop. There's basically just the one. We take some A, we're going to output some A. And that is parametricity. Parametricity means a little bit more when we're talking about functions that have more than one type variable in them, right? And maybe we'll get to that in a little bit. All right, and then we have ad hoc polymorphism or constrained polymorphism. I don't like calling it ad hoc polymorphism, but that's what everybody else seems to call it. So that means that the polymorphism is constrained by a type class, such as here, right? So this fat arrow here, right, tells us that there's a type class constraint on these variables. So where ID can be applied to a value of any type in the universe, this one can only be applied to types that have an instance of num. So we've constrained or limited the number of types that we can use addition with. But at the same time, we've got some information about them now, right? We know something about those types that allows us then to do more things with them. Okay, so there's a kind of inverse relationship here where the less you know about a type, kind of the less you can do with it, but then it can be anything, right? And the more you know about it, whether it has, so the stack is kind of like, parametric means it could be any type, but you can't do very much with it. Constrained means there are fewer types it could be, but you can do more things with it. You know more about it, and so then you can do more things with it. So there are more things that you can do with a num A to A to A, than you can with an A to A to A. And finally, with concrete types, then you've really limited what type the value could be, but generally speaking, there's more you can do with it, because you have even more information about what type it is. Okay? All right. Oh, we already talked about that. Yes. So if we did have, oh, here we go. All right, so this is what I was just saying. When we have a function that has the type integer to integer to integer, we have arguments of only one type. When we have a function like addition that is num A to A to A, then there are several types that it could be. And when we have it fully polymorphic, A can be any type, as long as the A's are all the same type, right? Because A has to always equal A. But what can we do with this function at the bottom? What could this be? How many implementations of this are there? Remember, it has to always behave the same no matter what type it is.
You can return the first one or the second one, I guess.
Could do identity of the one of the two.
Right.
That's pretty much it. Right? We can return the first value. Right? We can return this A, or we can return this A. But there's really nothing else that we can do here because we don't know anything else about A. Right? Now, like I said, parametric polymorphism is a little bit more useful when we have more than one type variable, right? Because, for example, in something like this type signature. This is a type class constraint, right? For the foldable type class. The sort of canonical foldable thing is lists or binary trees or similar data structures, right? And so if you want to, it's a constraint on the T, but only the T, right? So the T is here. So if you want to think of this as being a list of A, that's not inappropriate, right? The rest of this, right, A to B to B, and the B that returns, are unconstrained. They are parametrically polymorphic, right? But we do at least have two type variables here, right? So that our function that we're folding over our list or whatever doesn't have to be an A to A to A, like addition, right? We can do it A to B to B, but this gives us quite a bit of freedom, right? We don't know very much about what these types are. And we can do stuff, we can use addition there, right? Folding it over a list, in which case we've introduced a certain constraint, right, on that function itself. But for right now, we have no constraints to what this can be. Yes?
What's the significance of the parens in that first set of arguments there?
The significance of the parens there is that our first argument to foldable itself has to be a to fold R, sorry, has to be a function. Okay, so we haven't talked about how type signatures get parenthesized yet. Maybe I should have done that first. All right.
And similarly, is that the last T a type?
The last T, this?
Yeah.
Yes.
Okay.
So there's a bunch of different types that have foldable instances, just like for num. Right.
So the A and B don't have to.
They don't have to be foldable.
They don't have to match those
Right.
signature.
Right. The constraint here is only on this T.
Okay.
All right. So when we were talking about the function type, and we were talking how it takes one argument and returns one result. So in this case, this is our A, right? Our A argument. And we parenthesize it so that we know that the A argument in this case, the first argument to our function has to itself be a function. And we can further parenthesize that, of course, because really it is also only takes one argument and returns one result. We're going to copy that and not type it. Okay. So this should really have another set of parentheses there, right? And then this is our result type, right? This is our B of our function. And so if we fully parenthesize it, it would look like that. But having this set of parentheses here says that our first input has to be a function. And then we're gonna
You're missing a closing parenthesis.
Yeah, you're missing a close.
On the left.
Do I need
After the
one?
second B.
Huh?
After the second B, you're missing a closing
Am I?
parenthesis.
Left.
Oh yeah, there we go. Oh no, I actually want
No,
to.
back
Yeah,
there.
right there, right there.
Yeah. Yes. Right. So our first argument to fold R is a function, and then a B, then a foldable list of A's. I just said a foldable list of A's. a foldable of A's, and then it's going to give us back a B. Right. So when we use that, it looks like this. Right. So we've given it an A to B function here, or in this case it's actually an A to A, but that doesn't matter. So there's our A to B function. Here's our B, right? This little 0 is our B. That's our starting value. And then we gave it a foldable of A's to return a B. In this case, B and A are the same type, but it doesn't matter. Yes?
The TA bit, is that saying that A is foldable Or is it saying the T is foldable and it'll contain a bunch of A's?
Yes.
Or-
Yes, the latter.
Okay.
So the T has to be a foldable structure, a foldable data structure. So list, like I said, is kind of the canonical foldable. But there are a lot of other data structures you can think of that would be foldable, right? Binary trees, obviously, vectors, all kinds of things like that are foldable. We also actually have foldable instances for things like tuples and maybe. Controversially, we have foldable instances for them. But we do have them, so there's a lot of things that have foldable instances.
So that is function base case, foldable entity.
Yeah, this is it's not always your base case, but usually, yeah.
Right.
Yeah.
Plus corresponds to the A to B to B.
Right, plus corresponds to
Zero
the,
corresponds to the B,
yes,
and
the
the
list
list
is your T of
is
A.
A to B, and it happens to be T-able.
Your list is,
Foldable.
right, the list part is T,
Yeah.
and the values that are inside it are the A. Okay, so we could actually line that up, which we also were really OCD about doing in the book.
Wouldn't the A be the index and the B be the value stored in the index?
Wouldn't, I'm sorry, what? So the plus is your A to B to B. The 0 is this B. The 1 to 5 is your T of A. Right? So the list part is the T, and the values that are in it are the A.
And then the 15 that it spits out is that last B.
And the 15 that it spits out is the last B, yes.
Notice it'll be the same type as the B you passed it to 0.
Okay.
I'm sorry, what?
It'll be the same type as the B.
Yes, your result value, yes, will be the same type as this,
So,
this B here. And your function up here has to return a B. Right, it has to go from A to B. I'm trying to think of a,
could you
A to B to B.
huh?
A to B to B.
Yeah,
Yeah.
I'm trying to think of like an easy one though. I can only come up with things that I'd have to like write helper functions for. Adam, you got an A to B to B? Off the top of your head?
Show, or concat, in fact. You have a list of numbers, you feed them to a show, and then a concat.
Okay.
So your result would be string 1, 2, 3, 4,
Right.
5.
And the list reverse, that's a typical example.
Let me see if I can.
Because you can't just do, no. I don't know, I've never, show, because you're gonna have to, I also don't really want to give this a start value, but we're going to. I don't think that's gonna work. Oh, well, I left off the bracket, didn't I? I don't think that's gonna work though, no. With B to B, expected type.
empty
You gotta
string?
show and then concat.
Yes. Do I need to compose them? I don't know.
I might have to.
Huh?
The other way around.
Like that? Nope.
I had to create a lambda. You take 2 arguments.
Yeah, I
you
think that's
show
what
it,
you'd have to
and
do,
then-
yeah.
Okay.
Or, yeah.
So Sometimes I think,
Oh, 0 needs to be string.
It needs to be a string too, yeah.
Empty
Um,
string.
empty string, yes.
Yeah. But not, yeah, no, you'd have to, I didn't do it with the lambdas, okay.
Oh, well.
Yeah, like I said, I can't think of an easy one. People ask me a lot, and so I should just come up with an example that I can use, because people ask me that a lot. What's an A to B to B that you could do this with? Because most of them that you end up doing it with seem to be A to A to A.
I mean, you had to do a string concatenation with the.
Yeah, but you have to pass it in as, I think you have to pass in each thing to show individually, don't you? Yes?
I lost it.
Okay. All right.
What would say sequential for A to B to B?
Sequential?
Seek.
Seek?
It doesn't have a parenthesis here.
Yeah, but
No, so you'd have to map
I don't-
show to 1 to 5.
well, fold is mapping at the same time, right? Yeah. You guys, okay. Did you make it work yet? Oh, wait, let me think here. We've got like, no. That's not one. Oh, yeah.
Then you need to include cons as well, because it's inferring a char with the show.
Oh, yeah, well, because the type of show is A to string. So that's where it's getting the list of, that's where it's getting this from, right? All right. We need to, let me think about this. If we're gonna show those, because if we just map show over a list of numbers, what do we get? Like that, right?
Mm-hmm.
So we want to but yeah, show isn't an A to B to B.
No, it
Show's
isn't.
just an A to B. Well, it's an A to string, but which could be an A to B. So it's not binary.
You can use cons to doing the list reverse. That's a
But we could.
good example.
Yes. I think though that's still an A to A to A, isn't it?
Yeah, it's a
Yeah.
A to B.
Oh, right, because it's an A to.
Yeah.
Okay, so
A to
fold R. Yeah, but I mean that's kind of.
That's kind of the trivial case.
Yeah. I actually, yeah. It is, yeah. Because all you've done is fold the empty list over the list and return another list instead of, but it's not the same list, right? It's technically not the same list. Looks like the same list, kind of, but it's not.
If you,
create a lambda.
Oh, you want to reverse it?
Yeah.
So Then we have to flip the cons. I think it's like that, yeah. You have to flip the cons so that the arguments come in the right order, right? Because of the way fold L associates. There we go. That one's less trivial. That's actually how you implement reverse.
So next time you're in an interview and they ask you to reverse the linked list, you can just pull out that one-liner.
Yep. All right, any more questions about that? Okay. Do you want to talk more about folds? I didn't really prepare to talk about folds, but we can if you want. Yes?
We just started with the functions as arguments.
Yes. We did just start with functions as arguments.
Should we get another example of that?
Well, flip is another example, right? So we actually just had that. Flip is another example, but here flip takes an A to B to C, right? So potentially all three of those types could vary, and then it takes a B and an A and gives you back a C. So if you give it a function from A to B to C, such as cons is actually only A to list of A to list of A, right? But that counts for being A to B to C, right? And so,
Because it's a distinct list.
yes. And because, you know,
Does it mean?
cons is really sort of an A to B, right? Because these two things here are the same type, right?
Right.
So so this cons is really an A to B, but when we have things that are parametrically polymorphic like this, actually any type variable, they can be different types, they don't have to be. So if you see in a type signature A to B to C, an A to A is fine, is acceptable. Or an A to B is also acceptable. It's saying you can have a C, there could be a third type here, but there doesn't have to be.
Julie, so if you want to take the previous example out of the system, I think the problem was we weren't using the string concatenation, which is plus plus. If you use plus plus, you will be able to get a string for the list of numbers. Into
Oh, right, of course, yeah. Yeah. Thank you. I was thinking of the other kind of concat for some reason, because somebody said concat, and that's what I was thinking. Okay. All right, so this one too for flip also, and you saw that right here, right? Flip.
I just put together something. So I created a function GT5, which is compare if it's greater than 5. And then the fold R, my fold L is and compose GT5 6.10. And that works. So.
I have to still use let because I don't have.
Right.
Okay. Fold L.
No. It's that's a separate function. So that's just paren.
Right.
Greater than.
Oh, right, because you just.
Other way, but yes.
Like that?
Uh-huh.
So you just made a partially applied.
Right.
Okay, and then you did. Let.
Fold R, paren, and double ampersand.
Fold R, paren.
Double ampersand. Close paren, dot, GT5, close paren, true. List of 6 to 10.
All right.
There, A to B to B.
There we go. So the type of ampersand composed with GT5 is indeed A to B to B. Yay, Adam.
And in fact, you could just replace GT5 with the same definition. You wouldn't even need
Yeah.
to do the WAP.
Yeah.
So,
No, you wouldn't. You could just put it in there, parenthesized. All right, so if you want to look at, let's see here. I have, all right, so if we look at this, I know it seems like a lot. It's not. It's not such a big deal. All right, we have up here at the top a sum type, right? Now notice that when we did our sum type, because when we derive things like an ORD instance here, ORD will put them in order by default in the order that they're enumerated, right? Okay, so and here we have a function that takes two employee values and gives us a sentence that one or the other of them is the boss, right? All right, this is going to compare them, right? So this is going to take two employee values and also return a string, right? We're going to compare here. We're going to compare these two employee values. That's what the E variable and the E prime variable represent, right? These two employee values, that would be the input, right? So this here, if you're not familiar with it, this is a case expression. So it allows us to have three different cases and have different outputs depending on the case, right? So when we compare them, compare returns, these are the return values of compare. Greater than is GT, right? EQ is equal and LT is less than. All right, so in this case, if E, the first employee, is greater than the second employee, then it will use the function report boss, right, to say E is the boss of E prime. If they're equal, it'll say neither is the boss. Period. And if they're less than, if the result of comparing E to E prime is less than, then it's going to flip report boss. Right, so that's flip that we just saw. Right here. Okay. And flip has this type, right? So flip here is taking this function A to B to C, or in this case it's really A to B, right? Employee to IO unit as its first argument, right? Then here it takes a B value and its A value for that function, and will give us back the IO unit, which is there. Okay, so this time it'll flip how report boss works, right? It'll flip the two arguments of report boss so that it'll say that, E prime is the boss of E. So this one up here will say E is the boss of E prime. The second one will say E prime is the boss of E. Does that make sense?
Is that just always the preferred way rather than saying report boss, E prime E? You should just get used to utilizing flip like that?
It's not necessarily, no. No, you could do either way. So it's just I happen to remember, oh hey, I have something that actually has flip in it, and so yeah.
Where
What?
is GT, EQ, and LT values?
Those are the values that result from the compare function. Mhm.
And the compare function is built in?
Yes. It's in ORD, I
Okay.
think.
Mhm.
Tools. Yeah, it's right there. Right. So it returns what's called an ordering value, and those are G2, GT, EQ, and LT.
So I can't use those tokens anywhere else.
Right. Not if you're using ORD.
Okay.
Yeah. Okay. And so this one here now, we've written another one that is also a higher order function, right? So employee rank was just a function that went from employee to IO unit. This one now is also a higher order function. It also takes a function as its first input. And that function is represented here by the very helpful variable f. F for function, right? And then the two employee variables are still represented by E and E, right? Because, so this whole thing here is this variable f. And this employee is this E. And this employee is E prime. All right, so now we have case f, which is the same function, right? E, and then here in each one of our case matching, we're going to, we have what it should do, right? Which are the same as up here. So what is this F then? Now the F could be a lot of things that go from employee to ordering, except for not that many things actually result in an ordering value necessarily. So one thing that we could do, right, is if we have this function here, coder's rule, which goes from employee to ordering, then we can use this function as the first argument, the F here. And it'll flip everything around, so it makes coders the boss of everybody.
So at that point, you could rewrite employee rank to reuse rank improvement with compare.
Yes. And you can see here we also have the underscore again, right? So if you get two coders, they're equal. A coder compared to anybody else is greater than. Compared to anybody else, any of the other three values compared to a coder, you're going to get less than, right? Because the coder is greater. Right. So that way you don't have to write a pattern match for every possible combination of values, right? You just use the underscore to say the only case we particularly care about is that coder be greater than all the others. But again, since we want coder and coder to be equal, we wanted to put the most specific case at the top, right? Because if we had like this one first, then coder would be greater than coder, which is a little weird. Does that make sense? Okay. All right, so any more questions about higher order functions then? Functions that take functions as an argument? All right, so when we have the function type, right? When we have the function type here, we had already talked a little bit about how since every function has to take one input and return one result, you know, the b could itself be a function, right? So when you have addition, for example, where you have a binary operation, right? You actually take in one a, and then you return a resulting function, right? That then has the result in. Does that make sense? Because I didn't say that very clearly, I don't think. So for addition, for example, oops, also apparently can't type. So I guess we should use the type. Where it's an A to A to A, this is actually, should be constrained by no. Let's just do that so that we're correct. All right. So we don't normally parenthesize it because they're sort of parenthesized by this, like this by default. And so we don't have to make the result type, we don't have to make these parentheses explicit. This sort of is the case by default because that function arrow takes one argument and returns one result. One argument, one result, and it is right associative. So this is how it would be by default. The only time we have to put explicit parentheses is when the first argument, when the A itself, or in like a really complex type signature, if your first argument is the A and then the second one is some function itself, right, then you've got to parenthesize that to let it know then that this thing by itself has to also be a function, right? But this parenthesization will happen, is just how it is by default. And that, of course, is called currying, right? So Haskell is curried by default, which is what allows us to do things like oops. This, and then apply add 5 to some other number, right? With addition, it's maybe a little bit difficult to see why you would care about doing this, but that's the default currying is what allows us to do things like that. Because we've given it one input, and so it just constructs a function anyway that's waiting for a second input, right? And so we can name that function if we want to. And in fact, you can write, oops, like this, right? So fold R, as we just saw a few moments ago, takes a function and a base, some kind of base value, right? And it's supposed to then take a list, right? But we haven't applied it to the list. So now we can. So, and that's actually pretty close to how the sum function, that's actually pretty close to how it's implemented in base. It's just a partially applied fold. Okay, any questions? Okay. We talked about this stuff. We talked about all of that. All right, so if there aren't any questions, and if you want to keep going for just a little bit longer, do you want to, or are you ready to stop? Have you had enough of me and Haskell? Okay. I won't blame you a bit if you have, so just tell me. All right, so let's talk a little bit about monoid. Does anybody know what a monoid is? What is a monoid? Yes, Shane.
Something with an identity and combine, a way to put two things together.
Right.
In a starting point.
Right, exactly. So it's a binary operation. It's an associative operation, right? So like subtraction is not a monoid, right? Because it's not associative. But addition is. So it's a binary associative operation with an identity element. So what's the identity element in the case of addition?
0.
0. In the case of multiplication?
1.
In the case of list concatenation?
Empty list.
the empty list, right? So those are your sort of three most kind of basic monoids, right? So in Haskell, we have a type class called monoid, helpfully. If you don't have an identity value, by the way, if you have a binary associative operation but you don't have an identity value, it's called a semigroup, which is a separate type class. That's what I was saying earlier about non-empty. Since it can never be an empty list, there is no identity, and so it can only make a semigroup. You can still concatenate them, but there's no, right, you can solve a binary associative operation, but you don't have an identity element. All right, so this is what the class definition for monoid looks like. You can see here that mempty is just a value, right? That's your identity value. Mappend is your binary associative operation. So it's an A to A to A. We won't worry about McConcat. We won't worry about that for now because it's not really. We just don't need to talk about it. All right. So one of the reasons I wanted to talk about this type class is because this is one of the places where the unique pairing between a type class and a type gets a little bit complicated. Why is that? What would the monoid instance for integer be?
That's true.
Huh?
It has more than one.
It has more than one, that's right. And that's a problem, right? Because if they have to be unique, there can only be one monoid instance for integer, right? So, when clearly there are two valid monoids, right? I'm not going to get too much into the way we deal with that. The way we deal with that is by using what are called, the way we deal with it right now anyway, is mostly by using what are called new types. So we basically just wrap integer in a different name, and then we write the monoid instance for that name. So we have a sum type, SUM, and a product type, but these are not the same thing as sum and product types as we talked about before, right? We have a type called sum and a type called, and they are in data.monoid, isn't it?
Yes, I think so.
What? Oh. Okay. All right, so now we should be, yes, here it is. All right, so right here, I mean, it says sum A, but that's what we use for integers or ints or any of the similar things that we want to have some kind of numeric monoid for, right? Addition and subtraction and so forth. So then we have a monoid instance, not for integer, but for sum. And the monoid instance for sum is addition. And the monoid instance for product then is multiplication, right? So product is another new type wrapper. So the thing about new types is that while they allow us to give a new name to whatever this A is, right? They allow us to give a new name to whatever this A is, but the underlying representation is exactly the same. So unlike, say, writing a new data type, say calling this data product A, where you would where then you're really creating a pointer to that type, so you have like a new pointer, and so you actually introduce the possibility of a new bottom, a new undefined, right, a new null, sort of. Then new types don't. Of course, whatever your A is, there's a bottom there, right? Because it inhabits all the types. It just doesn't inhabit new types because the underlying representation is exactly the same. That new type wrapper just sort of disappears at compile time, and there's no new pointers, there's no new bottoms, there's no anything like that.
Is this different than the type aliases?
Yes. Yeah, new type is also different from type aliases in, there are a few ways it's different from type aliases. One of the most notable is that type aliases don't allow you to write new type class instances for whatever type it's wrapping,
Okay.
but new types do. right?
Yes.
Yeah.
So another common example is I have a customer ID. And as far as the database is concerned, that's an integer. But if I just represent it as an integer in my Haskell program, I can add customer IDs together, which is absolute nonsense.
Right.
So how do you use that?
How do I use product? Okay, so, or some, right, sure, because they're the same. Let me think about that.
Say you have a list of numbers.
Huh?
Say you have a list of numbers.
Yes. Don't you do it like this, Adam? Not map,
No, it's M can,
because that just maps them. It's concat, right?
yes.
We'll give you that. Nope.
M concat map?
I think, do you still have to tell it what type? Because it's just some A.
Shit.
I don't know, I haven't actually used them in a while. And I should have prepared for this, but this was kind of last minute. We're gonna look at the book. There we go. There, mapend like that.
That's what I'm doing wrong.
Yeah. So if you wrap them like this, I mean, in fact, you don't really use summon product, as you can tell by the fact that I can't remember how to use them. In fact, you don't use them very often because we just have addition, right? So but that's how you use them. And then you can unwrap that by, don't you do it like this? Yeah. Yeah. Yes.
So what's the cool factor of monoids then?
What's the cool factor of monoids? Oh, we'll get to that in just a minute. Because the cool factor of monoids is not really the integer ones, you're right. All right. So the reason I wanted to talk about monoid is okay, the reason that we have, oops, that was exactly my question when we first started writing this chapter, was why we care about pulling these things into a type class, right? Like why, okay, so we've got addition, we've got subtract, or multiplication, we've got list concatenation already, right? Which is why you never use sum and product, because you've already got addition and multiplication there, right? So why do we want a type class like monoid?
So you can combine like monoidal operations safely.
Yeah, so you can compose things where the order of your composition doesn't change the value that results.
Right?
And also you can constrain the type constructor. So what you were saying about parametricity, right? That if you know that that's a monoid, you know that you can compose it, right?
Yes.
Yeah.
So yeah, so that if you know that it's a monoid, now saying that something is a monoid doesn't necessarily mean that there's already a monoid instance for it, right? Because if you make up your own data type, you may have to write a monoid instance that shows how to append them together, right? So like the instance for sum just tells it to add them together just like an addition, right? But the instance for your data type will tell them to combine it in other ways. So for example, the infix operator from append looks like this. which is actually, I think, one of the best infix operators in Haskell because it actually kind of looks like what it's doing, I think. Right, it's taking the two things and joining them, right, in some way. So if you look at, for example, I think it's in, nope. All right, so if you look, for example, in here, this thing here, this whole big subparser, right? You see all these little mapens? I have a monoid instance for this that allows me to join these commands and run one subparser over them, or run one parser over it, right? Because the monoid instance joins these into one, joins all of these commands into one thing that the parser can read. That obviously is not, well, since we have the monoid type class, then writing an instance that allows you to sort of combine things into one larger thing is usually fairly trivial. Not always, but the idea is already there, right? We've got this type class. Now the type signature is only A to A to A, but that means that the behavior has to be basically the same, right? Has to just be able to join these two things into another value of the same type.
What's the, that a dollar sign? And then an S, the parser S?
That is a dollar sign. That is the dollar sign.
Is that an operator?
It is.
It's apply.
Yeah, it's apply.
Apply, okay.
So it's basically it's a right associative function application. So it means that all of this stuff, all of this appending will happen first, and then the subparser gets applied to that. Does that make sense?
So I could change the order of email, add, phone, show.
What do you mean change the order?
Flip those lines, the order of those 4 lines doesn't matter.
The order of the 4 lines doesn't matter, that's right, because append's associative, yeah. Yeah, so the order of these lines doesn't matter. Having this dollar sign doesn't necessarily matter, but then we need to wrap this all in a big parenthesis. Right? The dollar sign has, in this case, has the same effect as wrapping all of this in parentheses, saying like,
okay,
do all of this stuff first, and then the subparser is going to run over that.
so you could put parentheses instead?
You could, yeah.
So why the dollar sign?
Why the dollar sign?
Was dot taken for something else, or?
Dot is taken for function composition.
Okay.
Yeah. And this is not the same as function composition, right?
Okay.
So,
Function composition is reversed from dollar. So
yeah.
it's-
Yeah. Why the dollar sign?
No, you just answered it.
Yeah. Okay. That was
Because
for
that
what?
was-
So you weren't asking why the dollar sign instead of parentheses. You were asking why the dollar sign instead of some other
Instead of
operator.
dot, yeah,
Okay. Yeah. People do ask me why the dollar sign instead of parentheses a lot, and it usually is just an aesthetic preference. Some people, when you get used to Haskell, the dollar sign can seem more readable,
Right.
but it's not necessarily if you're not used to it.
It just means you don't have to go and hunt for the closing parent.
Right. Which, you know, probably if text editors and everything were as good as they probably should be, then you wouldn't have to do that anyway, but.
Right.
And this one though is different, right? This is a different thing than this,
Okay.
right? This is fmap. It's the infix operator for fmap. Yes?
How do you bring that infix append into scope? Is it import or something, or is it just always there? I'm trying to use it.
Import data.monoid, isn't it?
Yeah, it should be. I thought it was in scope now. No, isn't it in 8.1 though? Didn't they bring it in the Prelude now? But I don't have 8.1. Does anybody know? Anybody who has GHC 8? Because I don't have it on this machine, and if we wait here for me to install it, it'll...
So what are you trying to...
Isn't the append operator the infix operator from append? Isn't that in Prelude now? Because I think now I get conflicts with it because of the...
Yeah, it is.
Yeah.
Yeah.
All right, but if you have 7.10 or anything older, anything before 8, I think you have to import data.monoid to get the infix operator.
Great, thank you.
Yeah. But I better do that this afternoon and get this one upgraded to 8. All right, so yeah, that thing there is fmap. In my applicative workshop, we're actually going to be looking at this code in some detail, if you're curious about it, but I just thought I would show you a case of where here's something going on with monoids that's not, I mean, it's trivial in some sense, right? You're just combining them into one larger thing that the subparser can parse, right? But that's the cool thing about monoids, for me. Okay, the other cool thing about monoids, and the thing that I actually wanted to talk about because this winter retreat is fairly heavy on category theory, and I don't know how many of you are already familiar with category theory. Anyone? A little bit? Okay, so my introduction, I guess, to category theory, because I was a linguist before I started learning Haskell, a linguist and a teacher before I started learning Haskell, so I was not a mathematician. I wasn't into CS, I wasn't a programmer, and I never actually heard of category theory before I started learning Haskell. So my first introduction to category theory was from noticing that you have sum and product types, right? And they're addition and multiplication. And addition and multiplication are also the canonical integer monoids, right? And when you look at more monoid instances, like the monoid instances for maybe, there are several of them. Why are there several of them?
There are several types you can put inside a maybe.
Yes, because of the types you can put inside a maybe. But the pattern is basically, with monoids, that you get monoids of conjunction, where you're adding things together, right, or conjoining them. And you get monoids of disjunction, which, if you know, it took me a while to understand why addition is a disjunction. And I had to learn some things about set theory to understand that finally. And probably you all know more about that than I do. However, addition is a disjunctive operation. And so this pattern, I noticed that this pattern was all through Haskell. We have sum and product types, we have addition and multiplication, we have monoids of conjunction and disjunction. And the pattern is really consistent. And I got pretty excited about that and read a bunch of blog posts about it, and finally realized that it's because types, the set of types in Haskell is itself a monoidal set. It's itself a monoidal category. And so it itself has the same two basic monoids as integer, sum and product. Or I think, aren't they technically product and co-product, I think?
Yeah.
Yeah. And so that was kind of my first introduction to category theory, was realizing that this pattern is all over Haskell, the conjunction and disjunction, and thinking maybe there's a reason for that. And it's because types themselves, the category of types is itself monoidal, and so it itself has a consistent sum and product relationship. Types themselves do. Yes?
What's the identity type?
Um,
The ID value of types.
For, let me see if I get this right. For sum, it is void, the void type, which has no inhabitants. And for product, it's unit, which has one inhabitant. So for some types, the identity is, not that that comes in a lot of like, not that it really comes in handy for a lot of programming tasks to know that, but it's interesting for me anyway. So that's how I got interested in category theory, and I didn't know anything about category theory before I started Haskell. I learned the little bits I do know about category theory, because there's a whole lot I still don't know. But the little bits I do know, I actually learned through Haskell. So, and this was a very brief and perhaps slightly disorganized introduction, but I hope it'll at least help, particularly for those of you who aren't super familiar with how type signatures and stuff work. Any questions? Anyone? Okay. I will be around. I do have some more preparation for my applicative workshop that's happening tomorrow, in which I will not talk about category theory at all. We will talk about parsing, and we will talk about what's cool about the applicative type class, not the monoid type class, but the applicative type class. We'll talk about what's cool about that, because everybody thinks monad is really cool, but I like applicative, so I'm going to be evangelizing for applicative, and why it's cool, and then we'll look at some parsing. So I still have some preparation to do for that, but otherwise I'll be around. So if you do have questions, or you want me to go into more detail about something, I'd be happy to be here for that. Thank you.